Why don't skyscrapers simply crumble under their own weight? The answer lies in the fascinating science of concrete, the foundation of our modern world. From sidewalks beneath our feet to towers piercing the clouds, concrete is everywhere. But behind its gray appearance is a story of chemistry, physics, and human ingenuity. At its core, concrete is made from cement, water, and aggregates like sand, gravel, or crushed stone. When cement reacts with water, it goes through a chemical process called hydration. Tiny crystals form and bind the aggregates together, creating a rock-like material. The result is a substance that can resist enormous compression forces. In fact, properly cured concrete can withstand more than 10,000 pounds per square inch, which is like parking several cars on a single playing card. But here's the catch. Concrete is strong when squeezed, but brittle when pulled apart. It has almost no tensile strength, which means it cracks under stretching, bending, or twisting. That's why ancient Roman concrete marvels, like the Colosseum and aqueducts, while impressive, were limited in size and shape. They relied mostly on arches and domes to keep forces in compression. The breakthrough came with reinforced concrete, also known as RCC. By embedding steel rods or mesh, called rebar, inside concrete, engineers created a composite material that combines the best of both worlds. Steel is excellent at resisting tension, while concrete excels at resisting compression. Together, they can handle loads in almost every direction. This marriage of materials unlocked the modern skyline. Without rebar, there would be no skyscrapers, suspension bridges, or long-spanning highways. Consider this. The Burj Khalifa in Dubai, the tallest building in the world, required over 330,000 cubic meters of concrete and 39,000 metric tons of steel rebar. That's enough concrete to fill 132 Olympic swimming pools and enough steel to build 5 Eiffel Towers. Or take the Hoover Dam. It used so much concrete that engineers had to build special cooling pipes inside it. Otherwise, the curing process would have taken over a century to complete. But strength isn't just about the materials. Design matters too. Engineers carefully calculate how loads travel through a structure. Columns, beams, and slabs distribute forces so no single part is overstressed. That's why tall towers have massive foundations, sometimes spreading over an entire city block, transferring weight deep into the earth. Even the shape of a bridge arch or the spacing of support beams is chosen to keep concrete mostly in compression, minimizing the risk of cracking. Modern science has taken concrete even further. Engineers use admixtures, chemical additives, to fine-tune properties. Some admixtures slow down setting time for hot climates, while others speed it up for cold weather. Water-reducing agents make concrete stronger by packing the particles more tightly. Air-entraining agents add tiny bubbles, protecting it from freeze-thaw cycles in winter. There are even self-healing concretes that use bacteria or microcapsules of minerals to automatically seal small cracks before they grow. Durability is another challenge. Concrete is vulnerable to water, salt, and chemical attack, which can corrode the rebar inside. To combat this, engineers use protective coatings, corrosion-resistant alloys, or even fiber-reinforced polymers instead of steel. Advanced monitoring tools like ground-penetrating radar and acoustic emission sensors allow inspection teams to detect hidden flaws long before they become dangerous. Concrete has been with us for thousands of years. From the Romans mixing volcanic ash with lime to create structures that still stand today, to modern megaprojects like dams, tunnels, and stadiums. It's estimated that humans use more concrete than any other material on Earth, except water itself. Every year we produce over 10 billion tons of concrete worldwide, enough to build a wall around the planet 30 meters high and 30 meters thick. So, the next time you cross a bridge or stand beneath a skyscraper, remember, it isn't just a slab of grey stone. It's a carefully engineered system. Concrete carrying the weight, steel resisting the stretch, chemical science enhancing durability, and centuries of human knowledge shaping its design. Concrete is more than a material. It's the reason our modern world stands tall.